Now, I'd like to guide you in an animation of how step by step this would work. In this example, I'm actually going to show you how we're going to vaporize a liquid sample. Now, assuming that we have on this pipeline over here some liquid that's flowing through in the pipe, and we have a sample probe that is being installed, and it's going to be channeled into a heated regulator over here. And this heated regulator, if you notice that there is a enclosure over here that has this heater option, and it's demarcated by the red dotted lines over here. Now, first of all, we will need to turn on the heater to actually heat up the regulator. Now, once that is heated up, we can start to open the block valve over here to allow the samples to actually flow through the sampling line. Now we can observe that the liquid now has gotten into the heated regulator. So again, what this heated regulator is going to do, two functions, which is to bring down the pressure and also to heat it up so that it would be consistently in a gaseous phase. Now, once it has gone through the heated regulator, the vapor, the gas vapor in this case, as you can see in this animation, it travels in a much faster speed to your analyzers. So some of the analyzers which would be using this sort of liquid vaporizers, be it a gas chromatographs, O2 analyzers, or even spectrometers which are employing infrared, UV, or laser mechanism. Now, you'll be wondering what sort of advantages you'll be, in what kind of situations you'll be using a heated regulator besides vaporizing a liquid samples. Now, some of our customers who came back to us, they came to us and said that, hey, your heated regulator is not working because I'm still detecting liquids in my analyzer. What's going on here? These are what we call sometimes incomplete vaporization because the heated regulator was not sized correctly, that we have still pockets or partially some of the liquids still being carried over into the analyzers. Another common problem that our customers often come to us and complain would be fractionation. So the analyzers are actually reading components which are offset from each other because they have different specific gravities. That is largely also due to the inappropriate sizing of the regulators because the samples that are coming in are not cool enough that such that it is heated before it enters the regulator, and hence it causes pockets of light ends to actually vaporize off and push back the samples that's going through into the analyzers. Also, some of our customers often tell us that it's not acceptable that the samples are arriving to the analyzers a bit too late because it has jeopardized their process controls. Again, this can be resolved by having an appropriately sized heater regulator. And last but not least, one of the most common complaints we get from our customers are, my heater regulator is always damaged and we have to replace parts or replace the entire assembly of it. So good news is that if you're facing all of these difficulties, we do have a solution for you. It's our much improved KEV. Again, KEV is our model of our electrically heated regulator. some of these new improved features I'd like to highlight to you. Number one over here, as you can see, housed in the enclosure, the explosion-proof enclosure in this case, we have an updated PID controller. So this microcontroller have a new mathematical model that is much improved to reduce the chances of any temperature overshoot that might actually cause your heater to be damaged. But also we have improved the response time of the PID control algorithm such that it would be able to cater for a sudden surge of flow rate.
不是啦，这个是那个刷slow。
Oh, hello. We have someone here. Now, the next feature I'd like to highlight over here, it's our improved location of our temperature sensing device. So in this case, our sensor has actually be placed close enough in between the heater. As you can see, this is in red color, that's the heater block. And it is also close enough to the outlet of the regulator such that it will be able to sense both the heating temperatures and also the temperatures of the fluid that's flowing in the regulator. So we do have a good sensor over here. We do have a much improvised algorithm for the PID controlling. And we also have a thermal switch, which is automatically resettable in this case. What this thermal switch does is it does, especially when the regulator is housed in a heated enclosure, you do have a heated enclosure's temperature. Sometimes it might be too high. And when the regulator here senses that the ambient temperature is getting uncomfortable, it would automatically trip the circuit so that it would remove any heat that is going to be supplied into the regulator. Now, this resettable switch, another good thing about it, it's auto resettable, means that once the ambient temperature is normalized, it would reset back to its normal condition after I think a 30-minute period. And this thermal switch, since you can see that it's connected in parallel with a thermal fuse over here, so you still have the safety aspect of having a thermal fuse in this system itself, and it comes together with a resettable temperature switch. So you have two functions. They would be in an OR configuration. So either one takes precedence, it would automatically safeguard your entire heated regulator. So you don't have to worry about overheating your regulator and cause damage to it, and you would have downtime on your system.